Can a simple closed curve really divide the plane into two distinct regions? And why can't a surface be continuously deformed into a different dimension? Let's uncover two deep results from topology. To a kindergartner, this is trivial. You draw a circle on a piece of paper, point to the middle, and call it the inside. You point to the rest of the paper, and that's the outside. But in advanced mathematics, we cannot rely on human eyesight to prove that a boundary actually exists. We have to ask, how do we algebraically prove that a continuous loop forms an inescapable fence? Trusting human intuition in topology often leads straight to paradoxes. To understand what separation and dimension actually mean, we have to strip away our visual biases and rebuild the rules of geometry from bedrock. Our guide for this derivation is James R. Munkres' classic textbook on topology. We are looking specifically at Chapter 10, which covers separation theorems in the plane. These two specific theorems, the Jordan separation theorem and invariance of domain, provide the mathematical proof that a space's dimension is a fixed, uncheatable structural property. But before we can prove why a flat two-dimensional plane is strictly distinct from three-dimensional space, we first have to prove that a simple 2D loop actually functions as a barricade. Imagine drawing a continuous line on a plane that eventually loops all the way back around to its starting point. It seems entirely obvious that this line forms a closed fence. If you are inside, you cannot reach the outside without physically crossing the line. Yet topology allows for pathological spaces, structures that perfectly obey the mathematical rules of continuous functions, but completely shatter our visual expectations. This image shows the topologist's sine curve, a classic example of why visual boundaries cannot be trusted. As the curve approaches the y-axis, it oscillates infinitely. It is a single connected mathematical object, yet it never actually reaches its own boundary line at zero. This presents a serious problem. If a curve can fold infinitely without ever properly closing, how do we know our simple drawn loops don't contain infinitely small mathematical gaps that leak? Without a strict rule, we cannot assume any continuous loop definitively traps a point. We need a rigorous theorem to rule out these pathological edge cases. That solution is found in section 61, the Jordan separation theorem. The theorem starts with a strict parameter, a simple closed curve. In topology, this is defined as an injective continuous map from the unit circle into the 2D plane, meaning the line does not cross itself and it has no breaks. The theorem proves that this curve divides the entire plane into exactly two connected components, and the curve itself acts as the exact boundary for both of them. Geometrically, one of these components is bounded, meaning it has a finite area, while the other is unbounded, stretching outward to infinity. If you remove the curve itself from the plane, the remaining space is physically severed into two disjoint open sets. Any path connecting a point in the inside set to a point in the outside set is mathematically forced to intersect the boundary. The Jordan separation theorem guarantees that inside and outside are absolute, mathematically airtight realities. And with the 2D plane firmly locked down, we can examine the mechanics of higher dimensions. Now that we know how boundaries operate in a flat plane, we can ask a much larger question about dimension itself. This brings us to section 62, the Invariance of Domain theorem. Imagine taking an open subset, like an open disk missing its solid outer edge, in an n-dimensional space, and mapping it continuously and injectively. The theorem proves that the resulting image must also remain strictly open in that same n-dimensional space, and the mapping forms a perfect homeomorphism. This means you cannot crush or compress the intrinsic topological volume of a space. Its local openness is an indestructible property. To see why this matters, visualize what happens if we try to cheat this theorem and map our 2D open disk into a 3D world. As long as we map a 2D open disk onto another 2D plane, the open set is preserved perfectly. But if you take that exact same 2D disk and drop it into a 3D coordinate space, the geometry collapses. In a 3D universe, a perfectly flat plane has zero volume. Because the disk lacks 3D thickness, it can no longer contain a 3D open ball around any of its points. It ceases to be an open set in R3. If that openness is lost during the map, the foundational separation properties of the space, like those established by the Jordan separation theorem, are violated. Because an open 2D set ceases to be open in 3D space, a 2D surface can never be continuously deformed into a 3D volume. Dimension acts as an absolute, impassable barrier. Pure topology completely ignores rigid distances and specific shapes, yet it flawlessly identifies true structure. The Jordan separation theorem guarantees that boundaries are mathematically real and impenetrable, and the invariance of domain guarantees that the internal dimensionality of a space cannot be faked or flattened. Together, these theorems prove that dimension is a topological invariant, a permanent structural fingerprint of the space itself. While these proofs require heavy algebraic machinery to formalize, they establish the strict mathematical rules that allow us to define physical space, ensuring a flat plane and a solid room are forever distinct. Continuous injective maps will always preserve the foundational topology of our universe. If you found this helpful and want more clear explanations from standard books like Munkres, don't forget to like the video and subscribe to the channel.